All right, so might want to figure out what is the maximum or a minimum value of some objective function given some restrictions. Okay. So that's what our goal is. What is the maximum or a minimum value of an objective function subject to given restraints? You may recall from pre-calculus or even actually college algebra when I teach it too, you pretty much do the same problem all the time. You have a can in the shape of a cylinder. It has to hold a certain amount of volume. And that cylinder can be pretty much an infinite number of dimensions, right? It could be real tall and skinny, it could be real wide and flat, but the surface area of all those cylinders would be different, right? So you're making the cylinder, say a soda can out of aluminum, and there's a price per aluminum per square foot or something, or square inch, or centimeter, whatever it may be. So you want to minimize the cost, but keeping a certain amount of volume. So calculus comes into play with this. Those particular problems in college algebra and pre-calculus didn't require it, but now we have calculus for more complicated areas and volumes of whatever it may be able to figure that out. So we start off with an easy one. It's an area problem. So let's suppose P is equal to X times Y. And this is to be maximized. Subject to X plus Y is equal to 20. And so this could be represented as an area problem. It could just be a mathematical equation just representing two variables being multiplied, but the sum of those two variables cannot be anything but 20. So you can pick anything you want for X and Y as long as the sum is 20, 19 and 1, 18 and 2, and so forth, right? But then when you multiply, and this can be decimals too, I'm just picking nice whole numbers to work with to start off with, right? You'll be there all day long, right? You probably can figure it out just by not using calculus, but this is the procedure. So P, so we're going to rewrite P. So that it is in terms of only one variable. Using the information in the constraint equation. So if I say X plus Y is 20, you can just say that, hey, Y is equal to 20 minus X. Simple substitution. This is all this is. So now P is, and I put it in terms of X. So we always usually have functions in terms of X, right? You can do it in terms of Y. It doesn't matter, but this is just as easy. So P is equal to X times Y, but Y is 20 minus X. There we go. Which is equal to 20x minus x squared, put it in a polynomial format, because the next thing we want to do is probably what? Take a guess. Take a derivative, right? Now find p prime of x. P prime of x is going to be equal to power rule 20 minus 2x. Where do max and mins occur? At critical points. This is nothing new, right? So the next thing I want to do is what? Set this equal to 0. Twenty minus 2x equals 0. X would be 10, right? All right, so that doesn't tell me if that's the minimum or the maximum, right? But I know this is a critical point. Easy way to do is now find a bar large. P double prime and use a second derivative test to see if that leads to a max or min. Right? P double prime of X, that one's easy to do. Derivative of 20, 0, minus 2X is just negative 2. So P double prime at 10 is always going to still be negative 2 no matter what number you put in there. So this is a negative. This leads to a local max. That's in, right? So P of 10 is equal to 20 minus 2 times 10. Oh, wait. That's the derivative. That's the wrong one. The original. P of X was 20X minus X squared, right? So 20 times 10 minus 10 squared. So we got 20 times 10, this is 20, that's 200, minus 100 is equal to 100. So the maximum area there is 100. It's the maximum product of X and Y. So 10 by 10, right? All right, let's say you have 400 feet of fencing. One side is formed by a barn, requires no fence. We have 3 exterior sides and 2 interior sides. To form 3 partitions. Of a corral. What dimensions of the corral maximize the enclosed area? And what is that area? It's very similar to what we just did. Now it's just more to a word problem. And the picture is slightly different, right? But it's still an area problem with lengths of fencing. So draw a picture. Got your barn, right? You have 3 sides. And then you got 2 partitions on the inside to divide it up into 3 separate corrals. You want to think of it that way. I think I put this as section 4.4. I think it's actually section 4.5. I'll have to double check that. I'm using notes from an earlier edition, so my textbooks do when they change editions, they basically just change their section numbers. All right, so let's put some variables in here to represent these dimensions. All right, so each one of these, we got 4 vertical lengths, if you want to look at it that way, are all the same, right? They're all going to be rectangular. So let's say this one's X, this one's X, this one's X, this one's X, right? And this one over here would be length, let's say Y. It's different, right? But we know that X times Y is our area, right? Subject to, we only have 400 feet of fencing. So X plus X plus X plus X is 4 X's plus the 1 Y. Has to be 400. Actually, can't exceed 400. We can do less, but you know, use it all. All right, so after we come up with the area formula, what do we say we do? Just like we did in the last one. Get our optimization equation. So we optimizing this to be in terms of one variable. Let's put it in terms of X again. So therefore Y is equal to 400 minus 4X. So the area is equal to X times Y, 400 minus 4X, which is equal to 400X minus 4X squared. See? Derivative. A prime. Say of X, right? So function is in terms of X, which would be 400 minus 8X. 0 is equal to A prime. Gives critical points. Eight x is 400. X is 50. All right, so remember when we were looking for absolute maxes or absolute mins, we always evaluated the endpoints and also the critical points, right? Because sometimes those endpoints could actually be the absolute, the highest or lowest in that interval, right? This one's in real life thing. What can X go from? What is the possible domain of X? The smallest amount of X, just look at the picture. If you had no X's, 0 for X, that meant you had still 400 feet of fencing, right? But you can have 400 feet that is in horizontal. So you basically putting the fence flat against the bourne wall, right? And you can come out, say 1 foot, still have a rectangle, right? That's true. So anything after 0 is really what X can start at, right? So X being 0, let's just say 0 is an endpoint, right? So technically, we can start at 0. We have Y's. You don't have a rectangle in the case, but and I can go as high as how much X? How far out can I go while it's narrowing in? All the way, we got, look at your equation, 400X plus Y. If Y was 0, X could be all the way up to 100, right? So X could go up to 100 here. Would never exceed 100, actually can't even go up to 100, but just thinking as maximizing or minimizing anything, you always consider the critical points and their endpoints. So, wrote that part. So here are endpoints. So the absolute max will evaluate X and Y. X goes to 0. Y could be plugging into the original function. Go back and see. If X is 0, we said Y is 400, right? 400 feet, which gives a area of 0. Right? Then we go to the critical point 50. If X is 50, 4 times 50 is 200. 200 plus Y, 200 makes 400. So area is 50 times 200, which is 10,000 square feet. I think it was feet. I don't remember what the units were. And then I go up to the next endpoint, 100. That's if X is 100, Y was 0. So that's 400 times 0 is 0, right? So this one, just trying to point out that you always still should use endpoints. There will be some maximization problems where you have to evaluate the endpoints in there. This is just a kind of segue to that. Just to always, anytime you're looking for the absolute max or absolute min, that's what we're looking for in this case, the absolute maximum area for this particular problem, right? So that gives us dimensions of 50 by 200. with an area of 10,000 square feet. Fifty, 50, 50, 50, 2. Switch it forward. All right, so I've got a couple of more problems, actually 3 more, which I'm gonna leave that to the next class period because it's words, 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 words. By the time I finish writing the next one, we'll be done out of time. So we'll continue up on this section later on. I'll verify what section this is. I think on the syllabus, I think I had it listed as 4.4, but let's see. No, it's 4.5. This is section 4.5. Scratch that, right? Any questions?